Over the course of science, people have tried to comprehend how the universe started. The most broadly acknowledged explanation has been what many refer to as the theory of the Big Bang, an idea that proposes the universe began from an incredibly dense and hot point. Over time, various researchers have contributed evidence supporting this concept. However, as science advances and new technologies emerge, new ideas and perspectives challenge long-held assumptions. One such advancement comes from the James Webb Space Telescope, JWST, which has captured images of over 750 previously unknown galaxies. These findings are reshaping our understanding of the universe's beginnings, calling into question the accuracy of the Big Bang theory. The telescope was designed to help scientists understand how galaxies formed and evolved. However, its discoveries have revealed galaxies that are smaller, smoother, older, and more varied than what the Big Bang theory predicts. According to the theory, galaxies should appear larger the farther away they are, as the universe continues to expand. Yet these newfound galaxies defy this assumption. The Big Bang theory suggests that the universe began from a minuscule, superdense point known as a singularity, which was incredibly hot and composed of all the matter and energy that would later form stars, galaxies, and other cosmic structures. This theory is rooted in Albert Einstein's theory of general relativity, explaining that in the universe's early moments, all matter was compacted into an imperceptibly small space, creating an environment of extreme heat and density. For a long time, researchers believed this explanation provided the solution to the origin of the universe. However, new data from the JWST is now forcing scientists to reconsider aspects of this theory. The images from the JWST challenge the conventional view in several ways. For one, the galaxies it has found are older and more diverse than expected. They also appear far smoother than what the theory predicts. According to the Big Bang theory, galaxies should exhibit noticeable irregularities resulting from their formation and evolution over time. Yet these observations suggest an alternative cosmic history. Moreover, the distribution of galaxies observed by the JWST does not align with the predictions of the Big Bang, which anticipated galaxies to be less abundant in the distant past. The theory also suggested that galaxies would grow through collisions and mergers as the universe expanded, leading to a chaotic and violent cosmic environment. However, the JWST's images reveal galaxies that are more structured, with fewer signs of disruption or violent impacts. These observations imply that something about our understanding of how galaxies formed and evolved is incomplete. Despite these challenges, the Big Bang theory remains well supported by a wealth of evidence, such as the observed redshift in light from distant galaxies, the distribution of elements like hydrogen and helium, and the cosmic microwave background, CMB, radiation. All of this strongly supports the theory. The CMB, discovered in 1965, is a faint radiation that permeates the universe and is viewed as the afterglow of the Big Bang. Its uniformity and temperature distribution suggest that the universe once existed in an incredibly hot, dense state before expanding and cooling over billions of years. However, the findings of the JWST are prompting scientists to re-examine certain aspects of the theory. For example, the discovery of galaxies that seem to have formed much earlier than previously thought challenges the idea that galaxies should only have begun forming after a specific period following the Big Bang. The telescope's images show galaxies that appear much larger and more developed than expected, particularly at redshifts greater than 10, suggesting that these galaxies may have formed much sooner than the theory anticipated. These discrepancies have led some scientists to propose alternative models of the universe's origin, such as the cyclic universe model, which suggests that the universe undergoes an endless series of expansions and contractions. While these new theories present their own challenges, they offer intriguing possibilities for explaining the unexpected findings of the JWST. In addition, the JWST's high-resolution images provide remarkable detail on the formation of stars and planetary systems. By studying the light from distant stars and the surrounding gas and dust, astronomers can gain insights into the processes that govern star formation and the emergence of potentially habitable environments. This information is crucial for understanding how conditions necessary for life might arise elsewhere in the universe. Overall, the James Webb Space Telescope has provided a wealth of new data that is reshaping our understanding of the universe's history. While the Big Bang theory remains a robust and well-supported model, these new discoveries challenge some of its key assumptions. As scientists continue to explore the data from the JWST, They may need to revise our cosmic history and consider new theories to explain the unexpected complexities of the early universe. This ongoing research exemplifies the dynamic nature of scientific inquiry, where new evidence continually pushes the boundaries of our knowledge and understanding. The discoveries from the James Webb Space Telescope, JWST, are not only a challenge to the Big Bang Theory but also open new avenues for understanding the universe's development, the evolution of galaxies, and the overall nature of cosmology. The data collected by the JWST provides an unprecedented opportunity to reconsider the very foundations of astronomy, cosmology, and our place in the universe. This extended exploration delves deeper into the implications of these discoveries, how they challenge existing models, and how scientists are responding to these new realities. The James Webb Space Telescope, a new window to the universe, launched on December 25, 2021, is the most powerful space telescope ever built, a successor to the Hubble Space Telescope. Unlike Hubble, which primarily captures visible and ultraviolet light, the JWST is optimized for infrared observations. This is a key difference, as infrared light can penetrate dust clouds that obscure much of the visible light in space, allowing the JWST to peer into regions of the universe that were previously hidden from our view. The JWST's resolution and sensitivity far exceed anything that came before it. Its advanced optics and instruments are designed to study the formation of galaxies, stars, and planetary systems in unprecedented detail. This makes it possible to study not just the current state of the universe but also its early history, potentially offering new insights into how galaxies, stars, and planets formed. With this in mind, the telescope can observe galaxies at distances so great that their light has taken billions of years to reach Earth, essentially looking back in time. One of the JWST's major goals is to study the epoch of reionization, a period in the early universe that occurred around 400 million years after the Big Bang. During this time, the first stars and galaxies formed, and the universe began to transition from being opaque to transparent as light from these stars ionized the surrounding hydrogen gas. By studying this epoch, the JWST can provide crucial information about the conditions that led to the formation of the first galaxies and, more importantly, it can offer clues about how the early universe evolved. The universe developed into the organized and complex universe we notice today. New discoveries and their challenges question the Big Bang hypothesis. The theory of a prehistoric cosmic explosion has been the predominant model explaining the beginning and development of the universe for a very long time. According to this hypothesis, the universe began from an infinitely dense point, called a singularity, roughly 13.7 billion years ago, followed by rapid expansion known as the Big Bang. This event set the stage for the cooling and development of matter, which eventually coalesced into stars, galaxies, and the intricate structures we see in the universe today. For many years, the Big Bang theory was thought to have a robust framework. This was supported by several key observations: the discovery of cosmic microwave background, CMB, radiation, the distribution of galaxies across the universe, the redshift of light from distant galaxies, and the relative abundance of light elements like hydrogen and helium. However, the data collected by the James Webb Space Telescope, JWST, suggests that the early universe may have been more complex and evolved differently than previously thought. For example, the JWST has found galaxies that seem to have formed much sooner than expected, some only a few hundred million years after the Big Bang. This contradicts previous models that proposed galaxies took longer to form. Moreover, many of the newly observed galaxies appear to be more developed than expected for their age, with larger structures, more mature star populations, and more complex features than the Big Bang theory would predict for galaxies in such an early state. These discoveries are prompting cosmologists to reconsider the timeline of galaxy formation and evolution. If galaxies form so early and so fully developed, what does this suggest about the rate at which the universe cooled and evolved after the Big Bang? Was the rate of expansion faster than previously believed? Could there have been a different phase or condition in the early universe? Extra systems, for example, collaborations between dark matter, dark energy, and customary matter that we have not yet represented, contribute to the hypothesis of cosmic expansion, a still substantial, though fragmented, explanation. One of the key parts of the Big Bang theory is the concept of astronomical expansion. This hypothesis proposes that during the initial few minutes after the Big Bang, the universe expanded at an incredibly fast rate, far faster than the speed of light. This inflationary period is thought to have smoothed out any anomalies and set the stage for the slower expansion that followed. Expansion explains why the universe appears so homogeneous and isotropic on large scales today. It also provides an explanation for why distant regions of the universe have similar physical properties despite being separated by vast distances. However, inflationary theory itself remains incomplete. While it effectively accounts for the uniformity of the universe, it does not address the detailed formation of galaxies or explain how the initial density fluctuations, which would later evolve into galaxies and clusters of galaxies, emerged. These fluctuations are crucial to understanding the structure of the universe. JWST observations have revealed that some of the earliest galaxies exhibit features that challenge the predictions of cosmic expansion. For example, many of the galaxies found seem to have formed significantly sooner and developed more fully than inflationary models would suggest. This disparity between the theory of expansion and the actual observations from JWST leads some researchers to question whether expansion alone tells the full story. Could there have been another mechanism that triggered or accelerated galaxy formation in the early universe? One possible explanation could be the interaction between dark matter and regular matter in the universe's infancy. Dark matter is thought to make up around 27% of the universe's mass-energy content, yet it interacts primarily through gravity and not through electromagnetic forces. Its presence would have influenced the distribution of galaxies by acting as a gravitational framework around which galaxies could form. However, understanding the specific role of dark matter in early galaxy formation remains a significant challenge. Dark matter and dark energy, hidden forces behind galaxy formation. While JWST has made significant strides in providing greater clarity about galaxy formation, it has also highlighted the limitations of our current understanding of dark matter and dark energy. Dark matter, which does not emit or interact with electromagnetic radiation, has been indirectly observed through its gravitational effects on galaxies and galaxy clusters. Dark energy, on the other hand, is believed to be responsible for the accelerated expansion of the universe. One intriguing possibility is that the massive complex systems observed by JWST may have formed due to interactions between dark matter and dark energy. While we have a fair understanding of dark matter's gravitational effects, its interaction with normal matter and dark energy remains poorly understood. The JWST data, which shows galaxies that appear to have formed sooner and more fully than expected, may point to new interactions between dark matter, dark energy, and regular matter. It is conceivable that dark energy could have accelerated galaxy formation in ways we have not fully modeled yet. Reconsidering the timeline of galaxy formation. JWST's ability to look further back in time than ever before has raised questions about the timeline for galaxy formation in the early universe. According to the Big Bang theory, galaxies should not have formed until several hundred million years after the Big Bang, when the universe had cooled enough for matter to clump together and form stars. However, JWST has observed galaxies forming as early as a few hundred million years after the Big Bang, and these galaxies appear to be more mature than previously thought. One significant discovery is that some of these galaxies seem to have already formed massive structures, complete with star clusters, complex spiral features, and even signs of cosmic mergers, all before the universe was 500 million years old. This challenges the conventional understanding of galaxy formation, which assumes that galaxies gradually evolved from smaller clumps of gas and dust. These findings imply that either the rate of galaxy formation was much faster than expected or that some other mechanism, possibly involving dark matter or dark energy, contributed to an accelerated process of galaxy formation. The implications of these findings could extend to the concept of cosmic reionization, a period when the universe transitioned from being opaque to transparent. The early galaxies observed by JWST may have played a more significant role in this process than previously believed, as they could have contributed to the ionization of surrounding hydrogen gas earlier in the universe's history. This could mean that the reionization period happened much sooner than anticipated, potentially altering models of how the universe evolved from the Dark Ages to the more structured and luminous universe we see today. The cyclic universe model, a potential alternative. Given the unexpected findings of the JWST, some cosmologists are beginning to reconsider alternative models to the Big Bang theory. One such model is the cyclic universe theory, which proposes that the universe goes through an infinite series of expansions and contractions. According to this theory, The universe does not have a single beginning or end, but instead continuously cycles through phases of expansion and collapse. The cyclic universe theory has gained attention because of its potential to address some of the inconsistencies in the Big Bang model, particularly the challenges posed by the discovery of galaxies that appear to have formed sooner than expected. If the universe has gone through previous cycles of expansion and contraction, it's conceivable that some of these early galaxies were remnants of a previous cosmic epoch, not necessarily formed from the Big Bang itself. While this idea is still speculative and faces challenges of its own, it offers an intriguing alternative to the Big Bang theory. The cyclic model could provide a new perspective on how galaxies, stars, and other structures may have emerged in the early universe, and it might help explain the surprising findings from JWST.